Hi everyone, I'm Glezi Gutierrez from Geology 2102 and welcome to my research journal video. Today, I'm diving into a fascinating study titled Crustal Deformation Across and Beyond Central Europe and its Impact on Land Boundaries. This research was conducted by Kamil Maciuk and colleagues and published in Resources 2021. The study examines how tectonic plate movements affect cadastral parcel boundaries. It emphasizes the importance of precise measurements in managing land resources and ensuring the accuracy of land records. Specifically, the research highlights Poland as a case study, demonstrating how even small tectonic movements can accumulate over decades and impact land boundaries. In this video, I'll discuss the methodologies and tools used in this research, the significance of crustal deformation in land administration, and how this study relates to the Philippines, a tectonically active region. Let's explore how geology and geodetic engineering come together to address these challenges. Study background. Why it matters. Land boundaries are the foundation of property rights, land use planning, and sustainable development. Accurate boundaries depend on precise geodetic measurements, which are influenced by factors like tectonic movements, measurement errors, and geodetic control network accuracy. This study focuses on Poland, a country in the center of the European plate, making it an ideal subject due to its tectonic stability. However, even in such stable regions, tectonic plate movements caused by mantle convection, gravitational sliding, and other forces can gradually shift land boundary points. For example, the study found that tectonic activity causes boundary points to move by up to 0.13 meters over 25 years in Poland. While this is within the required cadastral accuracy of 0.30 meters, it underscores the need for regular updates to cadastral system to maintain precision. Methodology and data sources. Let's dive into the methods used in this study. The researchers relied on data from the European Permanent GNSS Network or EPN, which consists of 249 permanent stations across Europe. These stations collect precise positional data over years, allowing scientists to measure tectonic plate, velocities, and boundary point shifts. To ensure accuracy, the study used two reference systems. Number one is the International Terrestrial Reference Frame or ITRF, a global system capturing tectonic plate movements worldwide. And the next one is the European Terrestrial Reference Frame or ETRF, a regional system designed to minimize visible tectonic effects within Europe. The researchers calculated point velocities using long-term GNSS observations combined into a multi-year dataset. They employed mathematical transformations to account for translation, rotation, and scaling factors, ensuring that the results reflected true ground movements. Key steps in the methodology include collecting raw GNSS data from stations across Poland and neighboring regions, applying transformation to align data with the ITRF and ETRF reference frames, analyzing displacement vectors to identify boundary point shifts. Key findings and results. Boundary point displacement. Over a 25-year period, tectonic movements caused boundary points in Poland to shift by 0.13 meters, well within the required cadastral accuracy of 0.30 meters. Horizontal and vertical velocities. Horizontal movements were generally less than 1 millimeter per year in most of Poland, with slightly higher rates in the Balkan Peninsula and Turkey due to more active tectonics. Vertical displacement were also minimal, except in regions like Fennoscandia where post-glacial rebound caused a significant uplift. Comparison of reference frames. Using the ITRF revealed larger shifts, 22 to 25 mm per year compared to the ETRF, which effectively minimized tectonic influences for cadastral purposes. The study also highlighted the importance of periodic updates to cadastral data. In Poland, cadastral records are verified every 15 years to ensure accuracy. This approach could serve as a model for other countries, including the Philippines, where tectonic activity poses greater challenges. Application and relevance to the Philippines. Now, let's connect this study to the Philippines. Unlike Poland, the Philippines is located along the Pacific Ring of Fire, making it one of the most tectonically active regions in the world. Active fault zones like Philippine Fault Zone experience movements of up to 40 mm per year, significantly affecting land boundaries. This makes the lessons from Poland's cadastral system even more relevant. In the Philippines, regular updates to cadastral data using GNSS and INSAR technologies could help manage the impacts of tectonic activity on property rights and infrastructure planning. Discussion and future implications. This study underscores the importance of integrating geology and geodetic engineering in managing land resources. For tectonically stable regions like Poland, periodic updates and precise measurement systems ensure long-term accuracy. For active regions like Philippines, more frequent monitoring and advanced tools are needed to adapt to dynamic ground movements. Future research could focus on automating cadastral updates using real-time GNSS data or exploring how climate change-induced events like sea level rise interact with tectonic activity to impact land boundaries. Conclusion. In conclusion, this study highlights the profound connection between tectonic movements and cadastral accuracy. By analyzing Poland's relatively stable tectonic environment, we see the value of precise geodetic tools like GNSS in mitigating the impacts of crustal deformation on land boundaries. For regions like the Philippines, where tectonic activity is more dynamic, the integration of advanced geodetic systems with geological insights become even more critical. These collaborations ensures not only the reliability of land records but also contributes to disaster resilience, sustainable development, and efficient land management. This research is a reminder that even the seemingly slow movements of tectonic plates can have long-term consequences on our built environment. It's up to us, as future geodetic engineers and scientists, to continue advancing these technologies for a better understanding of our ever-changing planet. As James Hutton, the father of modern geology, once said, "The present is the key to the past." These timeless insights remind us that by studying Earth's current processes, we can better understand its history and shape a sustainable future. Thank you for watching. If you have questions or insights, feel free to share them in the comments. Don't forget to like and subscribe for more explorations into science and engineering topics. Again, I'm Glesy Gutierrez, your future geodetic engineer.